Correct sizing of a generator is very important. Light loading can lead to wet stacking and significantly shortened engine life. Engine manufacturers recommend engines do not run below 30% of full load for extended periods. On the other hand, using a generator too small for the load can result in unacceptable voltage drops and overheating. There are several factors to consider when sizing your generator. Application rating, standby or prime. A standby rating is for temporary power, allowing no overload, while a prime power rating allows for 10% overload for 1 hour in 12 hours running. Ambient conditions such as altitude, where there is less air for combustion, can reduce power, as can higher air temperatures and greater humidity. The manufacturer's duration charts should be consulted. Having determined any duration, the electrical characteristics of the load have to be taken into account, such as what is the voltage? Is it single or three-phase? Having determined the load characteristics, all the kilowatts of the various loads have to be totaled. Purely reactive or non-reactive loads, such as lights and heating, can be just totaled by adding up their power ratings. For reactive loads, such as electric motors, you have to take into account the additional power required on starting. In determining the size of a generator required, it is useful to learn a few terms commonly used in generator formulas applicable to reactive loads, and used to size electric motor loads. Commonly used generator formulas reference the following criteria: A for amperage, V for volts, kW, the symbol for kilowatts. Each kilowatt is 1,000 watts. kVA, which is the apparent power within a reactive load system. PF, signifying power factor, which is the relationship between kVA and kilowatts, the real available power. kW equals power factor times kVA. Single-phase power factor is usually unity, or 1 in 3 phase, usually not 0.8. The first formula to note is for a single-phase generator. For single-phase, the total kilowatts is a function of amps and volts. Amps, A, times volts, V, equals watts, or W. Dividing the watts by 1,000 gives you the kilowatts. The second formula to note is for three-phase generators. For three-phase, the kilowatts is a function of amps and the different voltage outputs of a three-phase generator. Again, amps equals A, V equals volts, but now we use root 3, the relation between the two voltages within a three-phase generator. We also introduce power factor, the difference between the available kilowatts and the apparent power, kVA, produced within the generator, shown as PF. The formula to determine kilowatts for a three-phase generator is given as amps times volts times root 3 times the power factor, which is usually 0.8 for most three-phase generators, then divided by 1,000 to give the kilowatts. In systems where a high percentage of the load is electric motor loads, it is important to consider the increased amperage to start an electric motor in relationship to the lower power to run the motor when it has started. Secondly, to ensure on a three-phase system, the loads are equally balanced on each phase. As for pushing a load from a stationary position, more force is required initially to overcome the inertia from stationary to moving. A typical motor can require up to 6 times the amperage to start as to run the motor. For example, a 100 horsepower three-phase motor is converted to kilowatts by multiplying by 0.746, requires 74.6 kilowatts to run. The amps to run is determined by dividing the kilowatts by the volts. Let's assume 208 times root 3 times 0.8, the usual running power factor for three-phase. We then have a resultant running amps of 259. However, on start, the amps can be 6 times running amps at 1,554 amps. On starting, we are overcoming the internal inertia of the motor and take account of the apparent power given as kVA, not kilowatts. As the relationship of kVA to kilowatts is power factor, we also have to take account of lower starting power factors of around 0.4 compared to a 0.8 power factor when running. Even with a lower starting power factor, starting kilowatts can average 3 times the running kilowatt requirement. When the system load includes multiple electric motors, the size of the generator set can be reduced by starting the motors in stages. When stagger starting, the motors try to start the largest motor first. Also note, some systems have motor starting aids on their electric motors to reduce the starting amps. Having taken account of the increased load on a generator to start electric motors, the next most important action is to ensure that on a three-phase system, all 3 phases carry an equal balanced amount of the load. A typical three-phase generator connected here in a parallel star three-phase 120 208 volt arrangement allows for the connection of single and three-phase motor loads. The relationship between the higher and lower voltage is √3. For 208 volts, connect A to B, B to C, and C to A. 120 volt single-phase motors can be powered by connecting A to N, B to N, and C to N. It is important to balance all three legs when connecting single-phase loads. To summarize, there are several factors to consider when sizing your generator. Does the application require a standby or prime power rating? Have you taken account of ambient conditions including altitude, temperature, and humidity? And have you used the manufacturer's duration formula? What are the phases and voltage configuration of the system? Have you taken account of all non-reactive loads such as heaters and lights? Small appliances can be included as they only have relatively small motors. Have you added all the reactive loads such as larger electric motors and calculated the power to start each motor? Have you taken into account any staggered motor starting to reduce the overall kilowatt demand? Have you ensured single-phase motors are balanced across the phases of a three-phase system? Taking account of all the points in this video will go a long way to ensuring you have a correctly sized generator able to reliably meet your load requirements.